forward mode AD, forward mode automatic or algorithmic differentiation. So if AD is not numerical differences, numerical approximation, if AD is not symbolic derivative, what then AD is? What does it do? So here's an example. Let's go back to our step 4 of the map, of the dynamic map that we're considering. Remember, the definition was L1 is x and Ln plus 1 is 4 L1 1 minus. Only, of course, there is no minus 1 there. Mm, That was our definition. So, well, we can just take and brute forcefully write the loop, right? For number 4, we start with 1 and go to 3, and we'll get our L4 because this is 1. This corresponds to L1 step, and then we go through the steps, iterate the map, and return the value L4. So look at what AD does. AD says instead of starting with V equals to X, what is the derivative of X? Well, it's 1, right? So we'll start with this tuple, with this pair of X and its derivative. It is easy to calculate the derivative at this point, right? We are using symbolic differentiation. So just an aside to the previous episode, even though AD is not numerical differentiation by differences or non-symbolic, all of the methods have the um, don't fall into tribalism of my method is better than your method. There is no point or there is no intention here. Every method has its own use and has it's just a tool. So here we do in AD we do use the rules thanks to Leibniz of symbolic differentiation to compute simple derivatives at each point. We just avoid computing complicated derivatives. And numerical differentiation by differences also is a good tool when you're developing AD systems. It's a good debugging tool because it's very easy to implement and you can always just throw more cycles and test your system uh, on numerical differences. So let's go back to the map. So what we do, we simply repeat what is happening here step by step, but in the following way. Uh, we take our function and our the derivative, but we evaluate the derivative at the previous point. So we plug in the value of the derivative from the previous step and the value of the function from the previous step into this next step calculation. And we calculate because we know what is this value numerically, right? So we have, yes, to simplify, we need to compute derivative of 4v1 minus v for 4v minus 4v squared. And derivative of this with respect to v is nothing but 4 dv. Remember the differential. Now we need it as ever minus 4v dv. So that's what is happening. dv, or this differential that we brought, we just plug in here. So, and also we plug in the value of x that we started with. And we can start, yeah, we are evaluating derivative at this point. And if we started, say, with x equals 1, just for example, then this whole thing will be minus 4. And then we started with x equals 1, then 4 times 1 minus 4 squared, 4 1 squared will be 0. And then this number now will go into the next iteration, and then we'll plug 0, plug 0 here. Well, that was a bad choice. Quickly converged to some yeah, it collapsed. Let's try something else, but you see where I'm going, right? Your x could be 2. Let's start with x equals 2, and derivative of x is still 1, right? Doesn't matter what its numerical value is. It's a constant. We started with, okay, now it is 8 times 2, 16. So 4 minus 16 minus 12 minus 12. But when we plug 2 here, 1 minus 2, 8. Minus 8. And then you continue, you take these values and come here again. So plug minus 12, minus 8, and minus 12. And keep iterating. In the end, you are returning numerical value of derivative together with the value of the function. This is forward mode automatic differentiation. Once again, what is happening, and don't get scared yet, we're not done. There will be more explanation. So we have this map, and of course, depending on this coefficient 4, if it's higher than 4, then you will get this nice bifurcations in this map, depending on the starting point and everything. So we have this map, and the goal is to compute derivative for L4. Manual differentiation, we can easily do that. Manual differentiation, we can easily do that. And then we can code it up and produce a function. This will be more of a manual approach. So we can code up the function or code it up in closed form and apply symbolic differentiation to the closed form, and we will get this function again. Automatic differentiation transforms our original function into something else. It does take as an input, like interface is the same, return value changed now. So instead of returning just the value of the function, it also returns the value of the derivative of the function. So that in one-dimensional case, that is simple. And numerical differentiation just returns difference approximation to the derivative. The key point is that automatic differentiation returns a value at machine precision, the same as the manual one. So if you are computing something with gradients, you can manually analytically differentiate your function and write a function that computes the derivative for your MATLAB or whatever for your solver, and then pass it on, and then the solver will call this function to compute the derivative instead of taking an approximation. Or your solver could have used AD, and every time it evaluates the forward of the function, it would obtain the derivative of it. The numerical value of the derivative, important to note here, not the derivative function. Um, it's a much harder problem, and plus, we don't need it. We only need the value. Here, assume our function is as simple as that. It's a function of two inputs, x and one output. So our f goes from R2 to R. And yeah, the Jacobian will be 1 by 2 vector, right? The gradient. So when we're talking about solving functions like that, think about compilers. How compilers would decompose this and construct. You need to store all of the intermediate values somewhere, right? So here's a computational graph of this function as a compiler would construct it. Say, well, going from syntax tree, parsing, and everything, but then in the end, down on the hardware, this has to be converted into computational graph. X1 and X2 have to be stored somewhere. So they are stored in these values, V0 and V minus 1. And then intermediate value of the product is here, V2, you multiply those two. And intermediate value of, uh, say, either sine or log, say log is here. Then you add them up together, log and sine, and the product has to be stored somewhere, the intermediate value, when it's not your compiler, it's not your code where you write like, oh, I don't have to store it in the intermediate value. But when it is computed, it has to be placed in some register somewhere on the raw hardware down beneath. And then the sine is computed here, and then we subtract, and here we go with our computational graph. We've got our result. Okay, now memorize that computational graph. Well, just kidding. So let's see what happens once again. So imagine x1 is 2, x2 is 5. We pass these values into here. They are obtained and stored in some intermediate register v minus 1 and v sub 0. Then v1 is our log. We can compute it and store it. We're here. This value is here, log natural log of 2. And then we compute the product, and then we compute the sine, we compute the sum, we compute the difference, and ta-da, in some intermediate register, the value was produced, and then we stored it in the output y, and returned 11.652. So 652,000, right? Thousands. Okay, now what is happening in parallel when we are computing the forward mode AD? So forward mode AD, what it does is, let's assume we want to compute derivative with respect to the first value, just the x1. And so what we'll obtain at the end is the first component of our gradients, right? We have our Jacobian contains of two elements. And so think of a basis in which this Jacobian lives, right? We have x1 and x2, well, sorry, and x2. So right now we're computing um, derivative along this dimension, right? What if what happens to y when the change happens along x1 dimension? So we'll put a value of 1 into the derivative of x, and we've put a value of 0 into the derivative of x2. Notice we could have done both, one here and one here. Then what we would have been like evaluating in this case, we would have been evaluating when both of them are 1, we are evaluating derivative along this direction. So just running a little bit ahead of myself, we're evaluating derivative of we're evaluating a directional derivative when we are evaluating forward mode AD. We could evaluate derivative along this direction as well by setting those values to 1 and -1 or -1 and 1. Um, but for now, let's focus on just evaluating one component of the gradient. Oh, okay, so V1, we know that we know the derivative, right? It's log of x prime, derivative is 1 over x times the differential dx. That's what is written here. 1 over x times the differential. What is that differential? We're bringing it with us. It's 1. Okay, let's plug it in and divide it by 2. Then uh, uh, the differential of the second differential v2 here, we're just going in strict correspondence. And again, what is the symbolic derivative of a product? X times y prime equals x prime y plus xy prime. Well, but in fact, this has dx, this has dy. So that's what we have. Mhm. 1 takes 5. Oh, okay. That's the thing. So because derivative of x is 1, so okay, derivative of is 1. Okay, that's why we have this. Then we go to v3 sine. Okay, it's cosine times the differential. The differential is back uh, to corresponding v0 and x2. So we get this 0 times something, and then the since we don't have any coefficients, right? It's just a plus b, so 1 and 1, only differentials play a role, and in the end, what this whole procedure returns, it returns numerical value, precise, up to machine precision, value of the derivative at this point with respect to the first component. And see how it is at this point, 2 and 5, because the values 2 and 5 do play a role. V0 is defined here, so they are connected. V minus 1 is defined there. So when this execution happens in parallel in You're computing both the derivative and the function value, and you return, okay, you're returning this and the derivative. So with this directional analogy and the derivative, the numerical derivative, I hope you see now that what this procedure is doing, the forward mode AD, it picks a column of Jacobian in a single path, So we have Jacobian of a function f, and that's what it is. Just all of the corresponding derivatives of every output with respect to every input component, every output component with respect to every input component. So that's why it is dimension of the output components by the input components m by n. So directional derivative is nothing but a product of this Jacobian times a vector. We're not actually evaluating it. The Jacobian is unknown to us. We are, in effect, what AD does, it evaluates this without actually expanding the Jacobian or constructing it. It's not doing element by element, but the result is effectively what's written here, because matrix vector is a matrix, and whatever you plug in here, you will get a directional derivative result. So think about the following. Now, when your function is, okay, you start with an x, single number, going through some complicated process function that returns multiple outputs, a vector of y1 through ym, and x is just one number. So your Jacobian in this case is just one vector, and your derivative, every component of your whole d1 by dx, the x is the same, so you go dy, d2 by dx, and you go through dy and by dx. In one forward pass, you are computing this whole, and I've transposed this, of course. You're computing this whole gradient when you have a function that takes one scalar and converts it into a vector. You're computing this whole gradient in one pass. If you add, say, second number here, so it's two numbers, x and x1 and x2. I just don't want to overload x1 and x2. Then you cannot just set one here and one here, because you will not be computing gradient. You will be computing directional derivative that is along the diagonal in the x1, x2 space. So you need to separately take another step and once again run the forward process and compute the second part of the second column of your Jacobian if you want the full output derivative. So this is a pain, and in the next episode we'll talk about how to, well, it took quite some years to figure out. Bert Spilpanning did it, but we'll talk about how to efficiently compute the derivative using backward mode AD when you're in a quite opposite situation. So when you are in this situation, you can do it easy when this is the function. But when your function is multiple inputs and one single output, then you need something else. We'll talk about that. But now here's an interesting curiosity or amazing ingenuity. So Clifford in 1873 introduced something called dual numbers. Now you represent your number as the sum, your number plus the derivative and an epsilon. So as long as epsilon is a non-zero number and has a property that when you square it, it equals to zero, the following operations are possible and the results that are generated are amazing. So take two dual numbers and add them together. So you add the like you cannot mix the differentials with non-differentials, so you separate them. So you add the sort of real part and the differential part. And oh, look, this is derivative of the sum. Okay, let's do the product. Let's multiply u times v, and when you cross multiply those two terms, you get epsilon squared, which is 0. It cancels, and look what you got. You started with two dual numbers, and you got another dual number with the I don't know what it's called actually, real part or non-differential part. But this is the product rule, just emerged from the way Clifford has cleverly constructed the dual number. And then other rules emerge as well. Function of a dual number is nothing but function of its real part plus the derivative of this function of the real part. So it's the compound function derivative or complex function derivative. Well, after the next episode.